Hello, everyone, and welcome to the Week 10 recording for COMP-111. So this is the lesson recording. We're going to just kind of tie up some loose ends tonight. So we're going to talk about how you would go about designing classes, the definitions of coupling cohesion. We're also going to talk about array algorithms and the efficiency of array algorithms and different things that you can do in that regard. Okay, so discovering classes. So remember, we've got those concepts that were back at the beginning of the class. We talked about the concept of encapsulation, which is the hiding of implementation details, right? So it's keeping things, in particular our instance variables, very protected. So we're not letting anyone have direct access to our instance variables. We're making them go through our methods to view them, to update them, and so on. All right, the other concept we talked about back towards the beginning of the class was abstraction, and this was keeping a class down to a single concept or a single entity. All right, so it's not having this big class called student that encompasses the student's grades and the student's financial aid and the student's addresses and the student's everything. It's keeping things to a single concept. So maybe you have their financial aid in one class, you have their current classes in another, you have their transcript in another, you have their addresses in another. So it's keeping everything to a single entity or a single concept. All right, so when we're trying to determine, so let's say you've been given this problem description and you're trying to determine, well, what should be the classes versus what will be the methods? Think in terms of noun versus verb, okay? Methods are taking actions, they're acting upon your instance variable data. So if you see something that's an action like calculate paycheck or calculate taxes, calculate is a verb, right? That's an action that you're going to take. That's going to be a method. If on the other hand you are paycheck, paycheck would be a noun. So you may have a class called paycheck, and then inside of paycheck you may have calculate taxes, calculate insurance deductible, calculate whatever. Those would be the methods inside of the class of paycheck. So this is how you go about when you're looking at a problem description and you're like, okay, what classes do I need? Look for the nouns. They're representing an entity, and then look for actions. Those are going to be the methods that you're going to need to act upon the data for that entity. All right, so taking a look at this example, we have a home business. You want a system that's going to allow you to keep track of customers, product inventory, and sales. So if we look at this and we try to identify the classes for this problem, immediately we need to look for nouns, okay? So home business is going to be the whole system as a whole, but we need to keep track of customers. So a customer is a noun, so that's going to be one class. We're going to need to keep track of our products. So product is a noun, that's going to be a class. We're going to need to keep track of our sales. What have we sold? What have we not sold? So that's going to be a class. And then our inventory may be tied into product. It may be separate. It just all depends upon how we want this to look. So you have the potential looking at this to immediately identify 3 to 4 classes that we're going to need for this particular solution. All right, assume you have a library and you need a catalog of all your books. So you want to keep track of books, DVDs, CDs, etc. You need to know all of your customers. You need to know which of the items have been checked out and by whom. So again, what would be the classes in this situation? So we need to look for the nouns. Library would be the system as a whole. Okay, so then customer is definitely a noun, so we'd want a class to keep track of our customers. We have these items that we're checking out, books, DVDs, and CDs. They don't necessarily need to be different classes. Like we don't need a book class and a DVD class and a CD class, although you could certainly do that, but you might have one class that's called an item, catalog item or something. Catalog is definitely a noun, and that's going to keep track of what items are available versus what items have been checked out. So those would be the primary classes that I would come up with initially: a catalog, an item, and a customer. Okay, so those would keep track of everything that we have, what's been checked out, what's not been checked out, and by whom. Right? And there may be some additional things that you come up with as you start working with the solution, but this is a really good start to get you going on this particular problem. Okay, so cohesion. So that's kind of discovering. So we're looking for nouns and verbs. Cohesion is how closely all the features in that class relate to a single concept. Okay, so how closely are we doing abstraction, right? The single concept kind of a feature. So you want high cohesion, you want things to be related to a single concept. So you really want to try to keep that a high cohesion. So consider the customer class. Which instance variables would be needed? So if you're thinking about a customer class, we're going to need to know the name of the customer. We're going to want to know the physical address of the customer, the email address of the customer, the phone, the fax number, maybe our sales contact. We might want to know that name, and then their particular phone number. We may want to know payment plans or discounts that are offered for that particular customer. So you start thinking about that, and then you start thinking, can any of these things be abstracted? Can any of them be taken down? So a customer might have an address, right? So we'd have that, and then our salesperson might also have an address. Maybe our salesperson's on the road or works, or maybe I don't know, there's other types of addresses. So an address could definitely be abstracted and become its own class. Maybe our customer has several branches. So we have our primary branch and then several other branches, rather than creating 4 different customers that are really the same. Maybe we create one customer with multiple addresses, one for each branch. Or maybe the customer receives product in one location, but billing goes to another location, and so those would be different addresses. So we could abstract out the address, make the address its own class, because an address is an address is an address, right? It's going to have a street, it's going to have a city, it's going to have a state, it's going to have a zip, and it doesn't really matter whether it's the address, the location where products should be delivered, or the location where bills should be sent. It's still an address. So that could definitely be abstracted out. And there may be other variables as well that you could abstract out and place into their own separate class. And these would make these items highly cohesive in that they're representing just a single entity. So think abstraction, cohesion, those would be the same. Okay, coupling. Coupling, on the other hand, is when one class is dependent upon another. So the customer class depending upon the address class, for example. Or if you think with regards to our labs, we have had different classes dependent on others. So in Lab 3, you saw some dependency. In Lab 4, you see even more. In Lab 5, even more under that. So you're seeing coupling here where a class is dependent upon another. The goal is to minimize coupling dependency. So you want low coupling, high cohesion. And I know that sounds confusing because we just wanted to go high cohesion, so we're pulling everything out, which then makes us dependent upon other classes. But I guess what you want to do is you want to look and really determine, is this dependency necessary or not? Is this beneficial? How is this going to serve? And that's where you come up with your low coupling versus high cohesion. All right. So we're going to go back a little bit about methods. If you remember way back in like week 1, week 2, week 3, we talked about methods, and there were 2 different method types, right? The mutator method, which changes the state of the object, in other words, changes the value of an instance variable. And we've been referring to these all along as set and get methods, right? And then the accessor method, which does not change the state of the object. It does not modify any of the values of the instance variables, but it does retrieve information. So that would have been our get methods. And also we've probably had some compute methods in our labs or calculate methods in our labs, different methods that aren't changing the value of any of the instance variables, but using our instance variables to produce different forms of output. So those would be our mutator and accessor methods. Mutator changes the state. accessor does not change the state. And when we talk about the state of the object, we're referring to those instance variables, the values of the instance variables. Well, in addition to have a mutator method and an accessor method, you can also basically have a mutator class or an accessor class. Now, we don't technically call them mutator classes and accessor classes. What we'll call it is immutable class. In other words, it's an accessor class. It accesses information only. It doesn't modify any data, so it has no mutator methods in it at all. And a prime example of this would be the string class that we've been dealing with throughout this course. I mean, really from day one, right? I mean, there's a lot of methods out there, right? There's the 2 uppercase, 2 lowercase, the substring, tons of others, index, replace, length, all of those different methods that we've been using throughout the course. But none of those changed the value of the string itself. It took that value, manipulated it, and gave you output, but the original value of the string remained the same. So even if we called the string.to uppercase, it gives us an uppercase version of the string, but if we went back and printed out that original string variable, it would still be in its original format, whether lowercase or mixed case or whatever. So the string class is what we call an immutable class. It has no mutator methods. There's no way to manipulate or change the original value of the string. Okay, so you can see we're just covering a whole bunch of little topics here. So we're moving on to side effects. So the official definition of a side effect is any kind of modification that is observable outside of the method. So we're not talking about changes that we make to local variables, right? Because local variables cease to exist when a method is done. So even if we change a local variable 100 times, that is not considered a side effect. It's something that's observable outside of the method. So local variables cease to exist inside the method. They don't count. So what it amounts to is changing the state of an object. When you change the state of an object, you've created a side effect because that is observable outside of the method. So if we call a set method that changes the value of an instance variable, we can then in turn call a get method and see that that instance variable has been changed. So it's observable outside of the set method. So that's what we mean by that. So there are both intended side effects. So when we call a set method, our intention is to change the value of that instance variable, right? So that's an intended side effect. But there's also some unintended side effects as well, and we're going to discuss those too. So side effect examples. So here we have reset dog. So we have this dog class out here, and we're going to reset it back to default. So we're changing the instance variables, and we know that because of the keyword this, right? If we say this.name, that refers to the instance variable of this particular object. So we're resetting these instance variables back to their default value. So this is indeed a side effect because we have changed the state of this object by changing the values of the instance variables. And we could observe this outside of this method because we could call the getName method and see that name is now assigned a value of unknown, and breed is now assigned a value of unknown, and age now has a value of 0, right? So we've changed the state of the object, changed the values of the instance variables, and this is indeed observable outside of the method. All right, copy dog D. So we have this dog D object coming in. We create a brand new object here, and this is a brand new local object. A brand new local object that's being created inside of this method. We set the name of our new local object to the name of our dog that was passed in here, this object that was passed in, and the breed and the age, and then we return this particular dog object that we've just created. In this particular case, this is not a side effect. We are not changing the values of the instance variables dog D. We are creating a brand new object here and setting it equal to these values. So while we're modifying this brand new object, it didn't exist before this method. So we're not changing anything. So this is not a side effect. We're creating a brand new dog object and we're returning it. Okay. Set name, we give it a name and we set this dot name equals new name. Again, this is a side effect. We're modifying the name instance variable. Get name, return this dot name. We are returning the value of the name, but we're not modifying it. So this is not a side effect. The instance variable, this dot name, is not being changed. It still contains its original value, so there's no side effect here. And here we have compute interest, so we're taking in two explicit parameters, amount and percent. We are calculating the interest here and returning it. This is, again, no side effect. This is a local variable that we're manipulating here and returning that computed value, but we're not changing the state of the object. We're not modifying the instance variable, so there is no side effect in this example. All right, now here is where we get to an unintended side effect. So here we're saying print dog, this dog D that's being passed in, and we're doing a print line, print the name, get the breed and print it, get the age and print it, and we're doing that right here. Okay, so this is what's called an unintended side effect. System.out object is being called by the printline method. This creates a dependency to the Windows console. The system.out.println method only works in a Windows environment. So if you have embedded system.out.println statements inside of your class, you've limited that class to only working in a Windows environment. And so this class can no longer be used on the web, on a phone app, or in any other circumstance. It can only be used in a Windows environment. And so this is what's called an unintended side effect. Now you're probably going, but wait, don't we want to print things out? Yes, you want to do that in your driver or your demo programs. So you want your class to be pure, right? You want your class to be able to be used in any environment. So maybe we create a Windows-based program that allows us to keep track of veterinary software, kind of pets and stuff. But we also create a phone app that does the same thing, and then we have a web program that does the same thing. Well, we could use the same dog class for all three of those as long as we have not limited it to working in any one environment. And then what you do is when you want to print reports, you would create a separate demo or driver program that prints your reports that would access the dog class and then would be specific. All right, I'm in a Windows environment, so my demo or driver program prints out to the Windows console. I'm in a phone environment, so I'm going to print out to my phone. I'm in a web environment, I'm going to print out to my client, to my web browser, kind of a thing. So this is what's called an unintended side effect because you've referenced a Windows feature here inside of a class, and now you've limited this class to only working in a Windows environment. Okay. That's it for side effects. Moving on to algorithms, in particular the total. So if we wanted to compute the total and we have an array available to us, we have two choices as to how we're going to go about that. We can define an instance variable to contain the total, and then every method that could potentially impact that total needs to update that instance variable. So for instance, every time we add a new item to our array, we need to also update the total. Every time we update a value in our array, we need to also update our total. And every time we remove something from our array, again, we need to delete that value from the total. Okay. The second choice is to just compute the total whenever we need it. So we would call a method that's called compute total or get total or something like that, and it would run through the array, add everything up, and compute the total. And so you might be asking, well, which one's better? Should I just have a total instance variable and every time I add, update, or remove, make sure I update that variable? Or should I just compute the total when I'm going? Which is better? It really depends. If you just have a small amount of data, like maybe your array is, I don't know, 1,000 or less in size, maybe it's better to just add it up every time to ensure that you're getting the most current data and computing your total. But if you've got an enormous amount of data, you've got millions upon millions of records, then you don't want to have to go through your entire array, a million hits to that array every single time you want the total. So in that case, you might go with the first option. And so here's how that would look. If we go with the first option where we have a total instance variable, whenever we add something, we would add that value to the total and then populate our array. Okay. Every time we update something, we're going to have to subtract what's currently in that position from our total, then add in the value that we're replacing in that position with the new total, and then set our position equal to that value. So if we're updating it, our array already contains a value and that's already been added to the total. So we need to first delete it from the total, and then we can add the new value to the total and then populate our array. And if we're removing something, then we need to delete it from the array and then null out our array position. So this was what it would look like if you did option number 1, where you're constantly updating the total to reflect the data that you have. Or you can just do a loop taking advantage of your next position that tells you where you populated your array, right? Nothing beyond next position contains a value, and you just compute your total right there at that point in time. And again, one is not better than the other. It just all depends, right, on how much data you have and how much data you have to process. All right, high, low. So this is a real common thing too, where you want to determine the lowest value in a range and the highest value in a range. So what you can do is you can set them both equal. So you'll create some local variables here, one called low and high, or whatever you want to call it, low value, high value, whatever makes sense to you. And we can set them both to the first position of the array, because right off the get-go, the very first value is the lowest, right? And I like to think of this in terms of having a stack. So maybe you have this stack of papers here that's got all of the exams that were taken for a particular class. And your instructor gives them to you and says, I want you to figure out what was the lowest score on the exam, what was the highest score on the exam. Well, you're going to flip over the very first one and look at it, and the very first one is both the lowest and the highest, right? Because that's the only one you've looked at. So you jot that down. Here's my low value, here's my high value. And then you flip over the next one and you compare its value to your low and compare its value to your high. And then, adjust as necessary, if at all. And then you keep flipping it over, right? Every time you flip it over. So I think of this low and high as you're jotting down on your paper what your low and high values are. You've got your loop is flipping over your papers each time, right? And we keep going as long as we have papers, and we check it. Okay, this is the score I have now. Is this less than my low? Because if so, it's my new low. Is this greater than my high? If so, then it's my new high. What I cannot do is put an else here and assume that if you're not my low, that you must be my high. Okay, these are two separate conditions. They have absolutely nothing to do with each other, so they should be their own if statement. If you're less than my low, you're now my low. If you're greater than my high, you're now my high. If you put an else in there, you're going to end up with some false highs, all right? Because then you're going to say, well, if you're not my low, you must be my high. Well, it could be that your high is currently 97 and your low is a 6, and you get a value of 8. 8's not my low, but now you're like, oh, it must be my high. And so you wipe out your 97 with your 8. So you want to keep these as two completely separate if conditions and not associate them with each other. Searching. Searching is a real common thing as well. A basic search algorithm, you just start at the beginning of the array, hunting for your item, and as soon as you find it, you return it. Okay, so we'll start with 0, keep going as long as we're in a populated portion of the array. If what's in value I equals our search value, and of course if this is a string, we'd have to say dot equals or dot equals ignore case, but if we're searching for numeric values, we can just use the equal equal. If they are equal, return your position of I, return your index position. If they're not equal, you make it all the way through the loop and you didn't return anything, that meant that the value wasn't found. So you can return a -1 or whatever value has been determined to be returned if it's not found. Okay, so this is a basic, simple search algorithm. Starts at the beginning, works its way to the end, checking for a match. Okay, there's also the binary search. So the binary search, what it does is it divides things in half. Okay, so we said our left is our leftmost boundary, which is always 0, right? And our right is set to the array length. So yes, it's 1 greater than the boundary because the boundary is always the length -1, so 1 greater than the boundary, but we set our right to the array length. And then we say as long as the left is less than the right. So what we're going to do is we're going to keep dividing things in half. And so as long as our right value is still greater than our left value, there's something in the middle that we need to check. Okay, so as long as the left is less than the right, there's something in that middle area, then what we do is we add the two together and divide by 2 to give us a midpoint. This is the middle of our array to the best of our ability. I mean, obviously, if we come up with an odd number, we're not going to be exactly in the middle, but as close to the middle as we can get. And then we check, is our value at the middle, is what we have in the array at the midpoint, is that less than the value we're seeking? If it is, then we know that it's got to be above that midpoint. It's got to be on the right-hand side of things, okay? If it's not, if it's greater than that, then we know it's on the left-hand side of things, okay? So if our midpoint, the value at our midpoint is less than our value, then we're going to set our left equal to that midpoint. And then we're only going to check midpoint +1, so then we're only going to check from the mid up through the right. We've just eliminated the whole bottom half of the array, or the initial point of the array, and we only need to check the second half of the array. If our midpoint is greater than our value, then we're going to set our right to the mid because we've eliminated the whole back half of our array and we only need to check the front half of our array. And if it's not less than and it's not greater than, it must be equal, so we're just going to return the midpoint. Now, this is anticipating that your array is sorted in correct order. Okay, if it's not in sorted order, this isn't going to work. But it's assuming that it's sorted in correct order. Okay, and so if we've set our left or right, we're going to come up here and again double check, is our left less than our right, and then we're going to divide it in half again. So let's say we had 10 items and we originally checked position 5, but we determined it's somewhere in 5 to 10. We're going to add, so we set left to 6 and right is still 10, so we're going to add those together. That's now 16. We divide it by 2, that's 8. So now our midpoint becomes an 8, and we check, is what's at 8 less than our value? Because if it is, then it's got to be in either position 9 or 10. Is it greater than our value? Then it's got to be in position 6 or 7. Okay, and if they're equal, then hey, I found my value, and you go on. And so you keep doing this, dividing into, and dividing into, until eventually you find the value that you're searching. But again, this is dependent, of course, upon the array being correctly sorted in order. All right, this is my least favorite. So here we go, big O notation. So when you're writing all these algorithms and you're writing your programs and things, you need to analyze these algorithms on occasion. I mean, if you're just working with a teeny bit of data, it's not critical. But if you're working with a large amount of data, you need to analyze it to see how efficient it might be. Some sections may be more labor intensive than others. Okay, and so that's what big O notation does, is it gives you an efficiency rating on the algorithms that you're writing. Just recently I was really struggling with some data. I needed to do some conversion data and the program was taking forever. Like I think when I took a look at it and was estimating, it was going to take like 48 hours to run, which is just not practical, right? To let something, I mean, it can run for 48 hours, but please. You know, like, why was it running for 48 hours? And so it was a ton of data, but we did a lot of different analysis, figured out where the biggest time hits were taking place, and were able to knock it down to maybe like 11 hours by creating some different efficiencies and knocking some things out. So big O notation allows you to really take a look at your algorithms, determine, you know, are they efficient, are they not, and figure out how you can make them more efficient. Okay, so when you're analyzing it, you count every operation, right? And some could be more labor intensive than others. Or you can account how often an array is visited, assuming that each visit to the array requires about the same amount of time. So when you're accessing an array, whether you're retrieving information from the array, setting something to a new value of the array, clearing something out, we're just going to assume that each one of those operations takes about the same time. So we're going with a worst case scenario here when we're computing our time. All right, so when you're doing big O notation, the steps to determine how efficient an array is, or the efficiency level of an array, is to first count the number of steps, drop the constants, different inputs equals different variables, and drop non-dominant terms. Now we're going to walk through these steps, but I would recommend, I have a couple of YouTube videos here so you can download the PowerPoint yourself. I recommend you go out to YouTube and just take a look at the big O notation. There's a lot of great information out there and a lot of pictorial type stuff that they can show you that can really help with understanding big O notation. Okay, so looking at the selection sort. If we were to look at the selection sort over here, and we were to do the big, huge, long formula, which is what I'm going here, but I'm going to show you a shortcut way afterwards, all right? But just show you what we're working at. N is going to be the size of the array. So we don't really know how big the array is, right? We have I equals left, I equals left, I is less than right, I plus plus I, and we've got our minimum. So N is the size of the array. So it's going to take us N visits to find the lowest value, right? So if we're thinking we just start at the beginning and work all the way to the end, we go worst case scenario, we're going to have to traverse the entire array one time to find the lowest value. Okay, so N visits to find the lowest. It's going to take 2 visits to swap value because we need to put whatever is in position 1 into 2 and what's in 2 into 1. So we've got 2 visits to swap. And then N minus 1 visits to find the next lowest because we know that one of them is the lowest. We don't need to check that one anymore. So N minus 1 visits to find the next lowest, and then 2 visits to swap those values, and so on. So if we assume that our array has a size of 5, we have N is the size of our array plus 2. So N visits to find the lowest, 2 swaps, right? And then N minus 1 to find the next lowest with 2 swaps. And then N minus 1 to find the third lowest with 2 swaps. And then N minus 1 to find the fourth lowest with 2 swaps. And then N minus 1 plus 2 to find the last value. So this would be the big formula that you would come up with to as to how many times you'd have to access the array. All right, so it equals this whole great big thing, and if we use our little math thing to get everything all, eliminate, so we've got N minus 1, and we take all of our 2's and add them together, and all of our minus 1's and do our thing there, and then consolidate this down, we end up with N times N plus N minus 1 times 2. Okay, so this is N number of N's, right? So if we go back to the steps that were back several slides on what we need to do with regards to big O notation, the first thing we do is we count the number of steps. So N times N is N squared plus N minus 1 times 2. Okay, so we have N squared plus N minus 1 times 2. Okay, next step is drop the constants. 2 is a constant, it's out of there. Okay, so we end up with just N squared plus N minus 1. Different inputs equal different variables. Ours are all the same input, so we only have one array that we're traversing, so we just have one input. And we drop all non-dominant terms. Well, n squared is a much greater value than n minus 1, so we drop the n minus 1 and we end up with n squared. And what we have is that the big O, the selection sort, scales on an n squared. So it scales quadratically as far as its efficiency goes. Now, different inputs equal different variables. So here's how I do this. So this is my shortcut way to do it. Count the number of nested loops. How many nested loops do you have? So different inputs equals different variables. So first look at how many arrays do you have. If you just have one array, it's one variable. Then count the number of nested loops, and that's how many you're going to be going here. So if you only have one array and one loop, your big O is O sub n. It's just a linear, you have to check everything one time, it's very linear. If you have one nested loop, so there's two loops in there because you have a loop inside of a loop and there's one array, it's going to be O sub n squared. If you have two nested loops, which means there's three loops, a loop inside of a loop inside of a loop, then it's going to be O sub n cubed. Okay, so much easier than doing this whole formula thing is just look for your variables. How many arrays do you, arrays or array lists do you have? If you just have one, then that's one variable. If you have two, that's going to be two variables. Okay, and then count your number of loops. One loop, you're just n. Two loops, n squared. Three loops, n cubed. Four loops, n raised to the power 4, and so on. Okay, now we've got a whole bunch of different things going on, and I just took this right from the book, so you can go out to the book and take a look. O sub 1 is a constant value. We have a logarithmic, we have linear, which is your one loop with the array, log linear, we have quadratic, cubic, exponential, and factorial. Now, one cute little story that I saw when I was researching big O notation, and you may think it's cute or not, I don't know, but this all started with the question, they said, which is faster? So if we put data on a USB drive, and we have two houses out there, and they're connected by the internet, and we also have a carrier pigeon. Okay, so we have this data that we want to get from house 1, from place 1 to place 2, okay, from house 1 to house 2, and they're, I don't know, 50 miles apart, okay? So the question is which is more efficient? As we continue to add data, which would be more efficient? The carrier pigeon taking a USB port from house 1 to house 2, or sending the data over the internet from house 1 to house 2. Okay, so if we're doing this, so the answer is actually that as you continue to increase data, the carrier pigeon becomes more efficient because it takes the carrier pigeon the same amount of time to fly from house 1 to house 2, regardless of how much data we load on that USB drive. But if we're sending things electronically, the more data we add, the longer it takes for the data to be transferred. So a carrier pigeon would be O sub 1, where it's a constant. It's the same amount of time to go from house 1 to house 2 carrying that USB drive regardless. I mean, I guess weather could come into play, but assuming all conditions are the same, it's going to take the same amount of time. It's a constant value for them, where transferring the data would be linear, and so it's going to increase with the amount of data that we give. So the larger the amount of data, the longer it's going to take for it to transfer. Okay, so last thing about big O and last slide altogether. All right, so if we have 100 pieces of data, and we know that in a linear environment, it takes 5 seconds to transfer 100 pieces of data. And in the n squared, the quadratic, it's 5 seconds, and in the cubed, it's also 5 seconds. So if we have 100 pieces of data, this is the time that it takes for it to occur in each one of these big O scenarios, all right? So if we have 200 pieces of data, then how long would you expect it to take? So in a linear environment, because 2 is twice the amount, or 200 is twice as big as 100, we would expect our seconds to also double and become 10 seconds. So 5 times 2 would be 10. And then down here we have 400. 100 to 400, that's times 4, so we would do 5 times 4, which gives us 20 seconds. So in a linear environment, it's pretty straightforward. However your data increases is however your time's going to increase. In the quadratic, what you're going to do is the difference from 1 to 2, it's multiplied by 2 times. It's a factor of 2. So we have our n squared, right? So 2 squared, it's a factor of 2. 2 squared times 5. So 2 squared is 4, so 4 times 5 is 20. It will take us 20 seconds to complete that in a quadratic situation. And 1 to 4 is multiplied by 4, so 4 squared times 5. 4 squared is 16 times 5, so that comes out to 80 seconds to complete it in the 400. Cubing really works the same way, but instead of squaring our value of 2 times, so remember 1 to 200, 100 to 200 is 2 times, so now we're doing 2 cubed, which would be 8 times 5, which gives us 40, and then 1 to 4 is 4 times, so now we have 4 cubed times 5, so 64 times 5 is 320 seconds. So this is how you could say, all right, well, if I've got this much data and my algorithm scales quadratically, this is how it's going to increase as I increase the data. If it scales cubically, this is how it's going to increase. And if it's linear, this is how it's going to increase. All right. And that brings us to the end. So certainly if you have any questions, do not hesitate to send me an email and ask. And other than that, that is the end of the week 10 lesson.